In this video, I'm going to explain the 2D Fourier transform. In some sense, the 2D Fourier transform is just a simple and straightforward extension of the 1D Fourier transform that you've been learning about so far. Unfortunately, however, it's not all that simple. Well, implementing the 2D FFT really is simple. The problem is interpreting the results of a 2D Fourier transform. And even more complicated is trying to predict what an image might look like based on its 2D FFT power spectrum. First, let me explain how pictures are represented on computers. When you have a picture like this, your computer represents this as a matrix. And the color in each little matrix element corresponds to a number. So in fact, the matrix looks like this. And you can see that larger numbers have darker colors. Now, when you have data organized in a matrix like this, the 2D FFT works by first taking a one-dimensional FFT along the columns of this matrix, and this produces a matrix of one-dimensional Fourier coefficients. And that you can see in this image. Frequency is on the y-axis. The top row is the DC component. And all of these values are Fourier coefficients for the Fourier transform from each column. The next step is to perform a 1D FFT on the rows of this matrix. The result of this step is a two-dimensional matrix of Fourier coefficients. In this matrix, the low-frequency coefficients are around the edges and the corners, while the Nyquist is at the center of the matrix. You'll recall that in a previous video I showed that in some disciplines people show the 1D power spectrum with DC in the middle, negative frequencies on the left, and positive frequencies on the right. For images, shifting the coefficients so that the Nyquist frequency is at the edge and the low frequencies are in the middle is almost always done. So typically the image power spectra are shown with low frequencies in the center, moving out towards higher frequencies and Nyquist in the corner. Computationally, that's really all there is to the 2D Fourier transform. What's tricky is figuring out how to map the features of an image onto locations in the 2D Fourier plane. And you know, when people teach the 2D Fourier transform, they typically jump immediately straight into showing power spectra of natural images. But I think it's better to start with really simple images and first to try to build a bit of intuition about how to interpret the 2D Fourier plane. Therefore, what I'm going to do in the rest of this video is show examples of how spatial frequency, phase, and location affect the 2D Fourier transform. In MATLAB, I've set up a movie to illustrate the relationship between frequency of a 2D sine wave and its representation in the 2D Fourier plane. Before running this simulation, I'll show you the layout of the main figure. So this is the image. It's a 2D sine wave, which is sometimes also called a sine plane or a gradient. You can see that along this dimension, it's a sine wave, and along this dimension, it's just straight lines. This is the 2D amplitude spectrum of this image, and this is the phase spectrum. And when I run this code, you'll see that the sine wave is going to change in frequency over time, as will the amplitude and phase spectra. And here what I'm going to do is hold the phase, which is the orientation of this gradient, constant, and change only the spatial frequency. This is like a real scientific experiment where you hold as many variables constant as possible and you change only one variable at a time in order to understand the effects of that variable independent of all the other variables. Now you can watch this video and you can see that as the spatial frequency of the sine waves increases, the peaks in the amplitude spectrum move further away from the origin. I'll run it again. You can also see some changes in the width of this peak, but this is actually not a really interesting feature. It's just due to the non-stationarities related to the spatial frequencies relative to the size of this image. You would see the same thing in the time domain in the amplitude spectrum of a sine wave that has non-integer number of cycles in the time window. The phase spectrum initially looks like it's changing a lot and like it's really granular and there's a lot of noise in it, but these are mostly just rounding errors, and you shouldn't pay too much attention to them. To understand where these come from, you can refer back to the video about interpreting phase values and the effects of uncertainty and noise when the amplitude is close to zero. And you see from the amplitude spectrum that the amplitude is basically zero almost everywhere on this plane. One thing I'd like to mention about the units of the spatial frequency that I have here. These are arbitrary numbers that I picked because they happen to look good on my computer screen. Depending on your screen resolution, these values may or may not look good. So I encourage you to play around with the lower and upper limits until you find something that looks good on your screen. This was for sine waves with one specific phase. And it's interesting to watch what happens when we change the phase of this 2D sine patch. Now I'll change the phase to be pi over 4. You can see that the orientation has changed, and importantly, the points on the amplitude spectrum are moving on the diagonal now instead of moving on this line here. But the behavior is exactly the same. They start close to the center, corresponding to low frequency sine waves, and then they move out towards the edges, in this case the corners, as the sine wave frequency increases. I encourage you to pause the video and experiment with other phase values and other spatial frequency ranges. Now for the next experiment. Here I'm going to hold the spatial frequency constant and change the phase values over time. So now the sine patch will be just rotating around as if it were the face of a clock. Actually, this would look pretty neat if this were the face of a clock. Now notice what's happening in the amplitude spectrum. The distance from the origin to the peaks is staying the same, but the angle relative to the origin is changing over time. So this experiment is complementary to the previous experiment. Again, I encourage you to pause the video and rerun the code with different values of spatial frequency and different sine phases. The third experiment is all about spatial location. Here I'm using a thresholded 2D Gaussian to create a ball that moves around on the plane. The size of the ball is constant, and therefore the spatial frequency of the ball is constant. Only the spatial location of the ball will change. And now running this code will show that the amplitude spectrum isn't really changing, but the phase spectrum is changing in a way that is, well, beautiful to look at, but pretty much impossible to interpret. What I mean by that is, if I just showed you this phase spectrum, you might be able to guess that the stimulus is a circle based on the spatial pattern of the phases, but you wouldn't be able to guess where in space the ball is. I'll tell you a little bit more about this code just so you know enough to be able to continue exploring it on your own. The circle is defined by this Gaussian and by this threshold, which varies between 0 and 1. This determines the size of the circle. And here, whatever values are subtracted off of the x and y matrices correspond to the center of the circle. So in this video, I introduced you to the 2D Fourier transform. I explained mechanistically how it works by applying the 1D Fourier transform first to the columns of a matrix and then to the rows of the resulting FFT coefficient matrix. I then showed several movies in MATLAB to help you understand the relationship between spatial frequency, phase, spatial location, and the results of the 2D Fourier transform.